Hello Math 1224, this is Dr. P with Lesson Launch 902. What's our vector, Victor? Bonus points if you get that reference. Also, not actual bonus points. It just means that you're cool. Anyway, in this video, I want to talk about how to translate from polar coordinates into Cartesian coordinates. In the last video, we took a point given in Cartesian coordinates and converted it into polar coordinates. That is, we expressed that point in polar coordinates. Now I want to go the other way. So we're given a point with polar coordinates 6, 5 pi over 6. And just as a reminder, when we write polar coordinates, the first coordinate always means distance from the origin, with one little exception, which I'll try to talk about at the end of this video. And the second coordinate means the direction of this point from the origin, expressed as an angle measure measured counterclockwise from the positive x-axis. All right, so we're going to take this information. We're thinking of a point here that is 6 units away from the origin and whose direction, whose angle measure from the positive x-axis is 5 pi over 6. Remember, everything here is in radians, and everything will be for the duration of this course anyway. So before I start putting this in Cartesian coordinates, the first thing I'm going to do, this is actually a first step towards putting it in Cartesian coordinates, is I'm going to draw a really good picture. I'm going to draw a picture of a coordinate plane, a Cartesian plane. There's my x-axis, there's my y-axis, and I'm going to draw a picture of where this point is. That point is 5 pi over 6 radians from the positive x-axis. Now, by the way, what is 5 pi over 6 anyway? I have a way of thinking about this that you may or may not find helpful if you have trouble translating 5 pi over 6 into an angle. So remember, if I'm looking at a coordinate plane, a full rotation, that's represented by a radian measure of 2 pi. So half a rotation would be pi. So pi is always from here to here in terms of angle measure. That's pi. So now I can just start subdividing pi into little chunks. Here I'm talking about 5 pi over 6. So if I were to take this and divide it into 6, well, what would 5/6 look like? Well, half of this would be 3/6, 1, 2, 3. And then 2 more 6 would be 1 and 2. So I'm somewhere over here on this ray here. That's 5 pi over 6. So I'm going to draw a point along that ray that I believe to be 6 units out. Of course, I can believe 6 units is whatever I want. It's my choice to make. I haven't specified what a unit is yet. But that's 6 units, and that is an angle of 5 pi over 6. All right. Now here, I'm going to use something that we might remember about the unit circle. I'm not going to use right triangle trigonometry on this. Instead, I'm going to use my unit circle understanding of the sine and cosine functions to figure out what the Cartesian coordinates of this point would be. All right. So one thing I remember from pre-calculus is that the sine of any angle, theta, or the sine of any angle measured, theta, in general, regardless of whether theta is between 0 and 90 degrees or not, that's always equal to y over r, where y is the y-coordinate of this point, and r is its radius from the origin. And I also know that the cosine of theta is equal to x over r. I don't know why I went in that order. That's kind of weird. But anyway, those are the generalized definitions of cosine and sine of any angle measure. And theta there can be anything. It can be between 0 and pi over 2. It could be greater than pi over 2. It could even be greater than 2 pi. This is always going to be true when I'm talking about the coordinate plane. So in this particular case, I can rearrange those equations and find that my x-coordinate is going to equal r times the cosine of theta, where that theta, of course, is going to be 5 pi over 6, and y is going to be r times the sine of theta, where again r represents the distance from the origin and theta represents our direction measured from the positive x-axis. So our x is going to be 6 times the cosine of 5 pi over 6, which I think, if I remember correctly, that's 6 times negative root 3 over 2. and that's going to be negative 3 root 3. And then my y-coordinate, that's going to be 6 times sine of 5 pi over 6. That's going to be 6 times, I believe that's 1/2, which gives me positive 3. Okay, and those coordinates do agree with common sense, in the sense that my x-coordinate is negative, as it should be. My y-coordinate is positive, as it should be. So I believe, based on all of that, that my Cartesian coordinates should be negative 3 root 3, comma, 3. And that seems pretty agreeable with this picture, because 3 root 3, that's larger in magnitude than 3, so I should be further out to the left than I am up. And that's what I seem to have here. Okay, so that's a way of doing that based on pre-calc formulas for sine of theta and cosine of theta. I realize that those formulas may still feel a little bit foreign. Another way I could have done this problem is I could have used a right triangle. Sketch this out. There we go, we draw the third side there. Okay, so I could use a right triangle and use this reference angle here, which is an angle of pi over 6. You might know that as 30 degrees. And then realize based on that that these side lengths here, this is going to be half of 6, that's 3. This is going to be square root of 3 over 2 times 6, that's 3 root 3, but of course that coordinate needs to be negative because I'm over to the left. So that's another way of doing it if these formulas don't quite feel cozy and comfortable to you. But these are formulas that I would like for you to know for purposes of this course, and also if you're taking multivariable calculus next semester for that course as well, you'll need them there too. So anyway, that's the idea behind how to find Cartesian coordinates from polar coordinates. Now, the one other thing I remember promising you is I promised I'd say a bit about what if this is negative, because that's not totally meaningless in this scenario. So here's what it means. If I talk about a point with polar coordinates negative 6, 5 pi over 6, our convention for what that means is we look at the same direction. So this is a ray at direction 5 pi over 6 here. But instead of going out 6 units along that ray, I go backwards 6 units. So I go out this way. That was supposed to be a dotted line. It's hard to do on a tablet. But this would be the point 6 comma, or sorry, not 6. That would be the point negative 6, 5 pi over 6. So in other words, a negative r coordinate in polar coordinates just means that we go backwards along a ray rather than forwards. Anyway, that's it for this video. As you can see, the procedure for converting polar coordinates to Cartesian coordinates is not too hard in terms of the algebra arithmetic you have to do. It's just there's this formula that allows us to make that transition. And understanding that formula is the key to understanding the whole process. All right, so that's it for this video. In the next one, I'm going to talk about functions expressed in polar coordinates. Should be a wild ride. Stay tuned.